Okay, as a little proposition, easy to show, if E and F are independent, only if and only if, then ECF and EFC and ECFC are also independent. This is if and only if so. Okay. All right, so we could show this. So probably the way to show this is proof. We'll do the first one. We'll show that EF independent implies ECF independent. So assume EF independent. So we can use that, right? Then we have PEC given F, using the definition, PECF. But ECF, okay, can be written as using the axiom about how mutually exclusive events are additive. Here is F, say, and here is E, and here is ECF. So I could write ECF as the probability of, so here I have, so here say I have the, this is EF, so I can write ECF as F minus the probability of F minus the probability of EF. So I have probability of F minus probability of EF over probability of F. And independence, right? By independence, this is probability of F minus probability of F times probability of E over probability of F. Okay, this is from independence. Our hypothesis in the proof, and then I cancel the P of F everywhere, and this is P of EC. So that's the proof. Okay, also, let's see, how would we define, how to define independence in among more than two. So we can motivate this with an example. Suppose, for example, we have, let's say E, first die is 2, F, second die is 5, and G, sum is 7. So this is roll 2 die. Okay, well, we just saw E and G, I called it F7, F sub 7, but E and G are independent. Also, F and G are independent. If I roll a 5 on the second die, the probability I get a 7 is 1/6 because I need a 2 on the first die to get a 7. So, all right, so in this case, let me use so we have E and G independent. E and F are also independent. This one we didn't just do, but you could probably check this. This is easy to show because, well, let's do it. So probability of EF, sorry, this should just be EF, the intersection here. This is equal to 1 over 36, right? It's the only outcome where the first die is a 2 and the second die is a 5. And this is equal to P, E, P, F, which is 1/6, 1/6. Okay, so EG is independent, EF is independent, GF is independent, but probability of G given EF is equal to 1. This is not equal to the probability of G. So all the pairs are satisfy pairwise independence, but as a triple, they're not independent. So another way to write this is, or P, E, F, G is just equal to P, E, F, really, right? It's just because you get G automatically. This is equal to 1 over 36. This is not equal to 1/6 times 1/6 times 1/6, which is equal to P, E, P, F, P, G. So we say, so E, the set EFG is a dependent set, is not independent. So you can be specific in these cases and say this set, the events in this set or the outcomes in this set are pairwise independent, but the set is not independent, something like that. So the definition, to be specific, is if E1, En are subsets of S, then we say the set E1, En is independent if and only if I'm going to use the double subscript here, EI1 if and only if the product of the intersection is equal to the product, the probability of the intersection of any subset is equal to the product of the individual probabilities of the elements in that subset for any subset of the big set. Okay, so if and only if this is true for any subset of, I'm being sloppy with the curly braces. I think it's okay. You have to. So if for any subset, if you want, you can, of the big set. Okay, so I need that to be true. So in the last example, it failed for the set itself, right? The set itself failed. All the pairwise subsets held, right? For any subset here of this. And just to be clear, we don't want single elements. Makes no sense to say one event is independent of itself or anything. So we would say for R can go from 2 to N here. Okay. All right. Okay. Well, we had to get those technicalities out of the way. And we'll see you on the other side.